So in this chapter, we'll be discussing solutions and properties of solutions and measurements of solutions. And so that's going to be important for um, some of the other topics we get to in this course. And it's important for chemistry because many chemical reactions occur in solutions. And so we need to understand these measurements and properties of them. So solutions are homogeneous mixtures, and they contain two or more substances. And so if you recall what it means to be homogeneous, it means that it's going to be the same throughout. So the solution is going to be consistent throughout the whole mixture. And a solution contains both a solute and a solvent. And so the solute is typically what dissolves in the solution, and it just means that it's going to be distributed uniformly throughout the solvent. And so the solvent is what usually does the dissolving. And so we typically have more solvent than we do solute. So the solute is typically not visible. But is usually what gives the solution the color that you may see. It may be colorless or it may have some type of color to it. And so we see in this picture here that we have mixed copper sulfate with water, and copper sulfate is the solute, that is what's being dissolved in the solution, and the water is the solvent. And so the water is doing the dissolving. And so we know that water is a colorless, clear liquid. And when we mix the copper sulfate, the solute, into it, it changes color. And that's primarily due to the copper ions. And so the solute is what's giving that solution its blue color. And as stated before, the solute is spread uniformly, it's distributed uniformly. So as you see in that picture, when the solution is mixed up, the blue solution is constant and consistent throughout the whole solution. And you can see also that before it was mixed, uh, the graduated cylinder on the left had the copper sulfate on the bottom, and so that was before it was mixed. And we can see there that the copper sulfate um, is in less amount. So we typically have less solute than we do the solvent. When we typically think of solutions, we usually think of liquid solutions, but they don't always have to be liquid solutions. We can have gas in gas solutions, so we can have a homogeneous mixture of gases, and one example of that is the air that we breathe every day. And so these the gas that's most abundant is nitrogen gas. The atmosphere is about 70 to 80% nitrogen gas, and so that's the solvent. And so all the other um, substances in the air pretty much considered the solute. And so the one that we usually are concerned with is oxygen, because that's what we breathe. We can have liquid solutions, and so we can have gas in liquid solution, we can have liquids in liquid solution, and we can have solids in liquid solution. And so um, gas in liquid solution, that would be an example, would be if you drink anything like soda or any kind of carbonated drink. And so what gives it its carbonation is carbon dioxide dissolved in the water. We can have liquid solutions, and so we can mix together two liquids. And in this case, they're given the example of vinegar. And so vinegars primarily water, which is a solvent, and it's mixed with acetic acid. And then we can also have solid in liquid water. And so you can think of things like salt water. And so we add salt to the water, and the water is a solvent, and we add a little bit of salt. Or sugar water, or if you like to drink sweet tea, you dissolve sugar in that water. And so the sugar or the salt would be the solute, and the solvent would be the water. And then we can have solid solutions, and so that's just homogeneous mixtures of solid. And so some things that you may think of is like something like brass, and brass is when you mix zinc with copper. And so here we're just trying to identify the solutes in these solutions. And so here we can compare sugar, 2 grams of sugar and 100 milliliters of water. So we're dissolving the solid into the liquid. And so the solid, the sugar, is going to be the solute in this case. In number 2, when we look at 60 milliliters of ethyl alcohol or ethanol with 30 milliliters of methyl alcohol or methanol, we have liquid and liquid solution, and so the easiest way to figure out which one's a solute is the one that's in less abundance. So we have less methanol or methyl alcohol, so that would be considered the solute. The number 3, we have 50 milliliters of water and 1.5 grams of NaCl or salt, and so the salt is the solute. We're adding the solid into the liquid. And then the last one, air, we have 200 milliliters of oxygen and 800 milliliters of nitrogen. And so we have less abundance of oxygen, and so that would be considered the solute. And so we can see that here. So typically, if you have uh, two of the same physical states, like liquid and liquid, solid and solid, gas and gas, whatever one is in less abundance or less amount, it's considered the solute. If you add anything to liquid, if you add gas or solid to liquids, the gas and the solids would be considered the solutes. Water is the most common solvent in nature. It's a very good solvent for many reasons. Um, it's a polar molecule, so if you may remember that, but there's an unequal sharing of its electrons in their covalent bonds, which creates those partial charges. And so we have oxygen, which is more electronegative than the hydrogens, and so oxygen will have partial negative charges, and the hydrogens will have partial positive charges. And what happens is that um, water is has a lot of hydrogen bonds because of those partial charges, and so we can see that in the diagram there. Just because, and so it's has those strong intermolecular forces between those molecules. Our bodies contain 60% water by mass, and that's good for many reasons. And so, we know that water is a good solvent, so it allows materials to be transported from one part of our body to another. Um, Water is has high specific heat, so it resists temperature change, which is good for our body because we need to keep our bodies in balance, in particular with temperature, because we know that when our body temperature changes just in the slightest, that we can be largely affected. And so, but water, our bodies contain mostly water, and which helps us transport a lot of nutrients and vitamins and materials throughout our body. So to form a solution, the solute and the solvent must have like polarities. And so what that means is that when we're going to mix up these solutes and solvents, in order to make a solution, they need to be of the same polarities or similar polarities. So we want to mix non-polar solutes with non-polar solvents. We want to mix polar solutes with polar solvents, and so that they are of like polarities. So we can also have ionic and polar solutes with solvents, and so um, ionic compounds can and will mix with polar solvents. Um, and so that is the case in this example here when we look at salt, NaCl. And so NaCl is an ionic compound, and so it's going to want to separate into its charges into Na plus and Cl minus. And so um, those charges are attracted to the partial charges to the water. And so the Na plus, the sodium has a plus charge, and it's going to be attracted to the partial negative charges to the oxygens in water. The chlorines are going to have a negative charge, and they're going to be attracted to the partial positives of the hydrogens in the water. And so salt is going to dissolve in the water, and so when it dissolves, we see that it changes state. Those solids are being dissolved into the solution, and when it does that, it separates or dissociates into its ions, and so ionic compounds are going to completely dissociate, and so they're going to completely separate into their charges into Na plus and Cl minus. And so we can see the reaction, the chemical equation here. And same thing here. So here we're looking at lithium chloride, and again, it's another ionic compound. And what we need to do in this learning check is to figure out which one of these is true. Why does lithium chloride dissolve in water? And so lithium is a metal, and it's going to separate into its charges, and it's going to dissociate. And so because it's a metal, it's going to want to become a positive charge. It's going to want to lose one of its electrons. And so we said before, oxygen is going to have a partial negative charge because of the polarity of the molecule. And so those opposite charges are going to attract. The positive on the lithium is going to be attracted to the partial negative of the oxygen atoms in the water. So A would be true. B, it states that lithium plus ions are attracted to the hydrogen partial positives of water. And so like charges do not attract to one another. Like charges repel. And so B would not be true. C, the Cl minus ions are attracted to the oxygen partial negatives of the water. And so again, we have like charges. Like charges do not attract to one another. They're repelled, so C would not be true. And D, the Cl minus are attracted to the hydrogen's partial positive. And so that would be true because they are of opposite charges, and opposite charges do attract. And so A and D are true, and so our correct answer would be choice E. And so we see that there. So we stated before that for solutes and solvents to properly mix with one another, we have to have of like polarities. And so methanol is another an example of a polar solute or polar compound because we have differences in electronegativity. So we have an unequal sharing of electrons, and which creates that molecule to be polar. And so if we mix methanol with water, they will mix and make a solution. And that's because they are both polar compounds there. And so we typically would have less amount of methanol, and we would typically have more water when we mix the two. And so the methanol would be considered the solute, and the water would be considered the solvent. And so, because they are of like polarities, they're both polar compounds, then they would mix and be able to make a solution. And so, um, Methanol can also make hydrogen bonds. We have, like I said, we have those differences in electronegativity, which creates those partial charges. So the oxygen in methanol is going to have a partial negative, and the hydrogen that's bonded to the oxygen would have a partial positive, very similar to how water makes its partial charges. And so you would have hydrogen bonding with methanol and hydrogen bonding within the water molecules. And so when you mix methanol and water, they create hydrogen bonds together. And so um, that makes some strong intermolecular forces and allows a solution to be made. So when we stated earlier that solute and solvents of like polarity will make a solution, the shorthand way of saying it is like dissolves like. And so when solutions or solutes and solvents have like polarities, they will be able to dissolve in one another. So like dissolves like. So a solid polar solvent will dissolve a polar solute. A nonpolar solvent will dissolve a nonpolar solute. And so, um, but when they are of unlike polarities, when we have a polar solvent and a nonpolar solute, they won't mix. So the examples that they give here is water dissolving sugar or salt. So sugar is a polar molecule, and salt is an ionic compound. And so you can pretty much group polar and ionic compounds together. And so if it's polar or ionic, it will be dissolved in a polar solvent. If And so that's because we have those charges in the solution, and they'll be able to interact with each other to create a solution. But nonpolar solutes will have to dissolve in a nonpolar solvent, and so we can mix oil with another nonpolar solvent, such as in this case hexane. Um, and so this kind of goes and shows why oil and water do not mix. If you put oil in water, you see that oil usually floats to the top. And that's because they are of opposite polarities. And so they don't interact with one another. They are not attracted to one another. And so that's why they do not mix. They are not of like polarities. And so here it's asking which of these solutes would dissolve in water. Why or why not? So here we have sodium sulfate, and sodium sulfate is going to be an ionic salt. So it's going to, the sodium and the sulfate are going to dissolve and dissociate. And so they're going to break up and separate into its ions. And so that would be able to dissolve in water. So sodium sulfate is ionic, water is polar. Ionic solutes can dissolve in polar solvents. In B, we have gasoline, and it says specifically it's nonpolar. So if it's nonpolar, uh, we don't have like with like. We have nonpolar with polar, so that's not going to dissolve. In C, we have I2. I2 is, there is no difference in electronegativity between the two ions, so it's going to be completely nonpolar, and so it will not dissolve in the water. And then D, we have HCl. And HCl is going to be polar, and so it's going to dissolve and dissociate. So that would be able to dissolve in the water. And so we can see that there, and it just says the same thing that I've just explained. So ionic and polar solutes dissolve in water because water is polar. Nonpolar solutes, such as gasoline iodine, nonpolar will not dissolve in polar, which is water. And so this kind of brings us into electrolytes and non-electrolytes. And we'll be discussing what these are and their properties. So when these compounds or polar molecules are dissolved in water, we can either create strong, weak, or non-electrolytes. And so when we have strong electrolytes, that means that the compound will completely dissociate in the solution. And so you make a lot of ions. You're going to make, so in the case here, we see on the left-hand side, we see NaCl. NaCl is a salt. It's an ionic compound, and it's going to completely separate into its ions. You will only have Na plus and Cl minus. And because they separate into its ions, then you will be able to pass electricity through the solution. And so that's what's being shown there, and that shows why the light bulb will light up, even though you don't have the connection to the um, connection to the light bulb. Those wires are not connecting in the solution. The ions are allowed to travel through the solution, and so the light bulb will light up. Weak electrolytes, they will separate into some ions and separate into some charges, but you will also keep some of the molecule intact. They won't completely separate. Not all of them will anyway. And so you do allow some ions to be able to flow through the solution, which would allow that light bulb to light up, but it's not going to be nearly as bright because you don't have as many ions passing through the solution, because it's not completely, the solute is not completely separated or dissociated. And then lastly, we have non-electrolytes. Non-electrolytes do not separate into ions at all. It's going to stay completely intact. It's going to stay as a molecule. You will not have any ions. And so in this case, you wouldn't have any electrons being able to pass through the solution. And so it will still dissolve in the solvent, but it will not have any charges. And so this case here, they're looking at sucrose or sugar. And so the sugar, we know that it dissolves in the solvent. We know it dissolves in water, but because it does not dissolve into its ions, then it's going to stay as a molecule and not allow electrons to flow through the solution, and so therefore the light bulb will not light up. So solutes that are strong electrolytes dissociate and separate into its ions 100%. And so all you will have is positive and negative ions in water. And so this typically happens with salts, all right, or ionic compounds. And so the solid dissolves and dissociates into aqueous solution. And so the physical state you see in the chemical equation, we see that it starts with an S for solid for NaCl and CaBr2. But then when it dissolves in the water, it becomes aqueous ions. And so you see the AQ in parentheses after the ion is written, and that just means it's aqueous or it's dissolved in water. And so we see also in these chemical equations that there is a single arrow pointing from the reactants to the products. And so that means it's going in one direction, and it's going to go completely from all those reactants are going to go all the way to the product. So there's only one direction. And so all we're going to be left with in water is with those ions, the sodium plus and Cl minus. So there won't be any of the solid salts remaining. All you will have is ions. And so that's why we show that as a single arrow. And so here it's asking us to pick what would be the correct way to show the products in these reactions, these chemical equations. And so looking at your periodic tables, you can see that calcium is in group 2, and so it's going to form a positive 2 charge. And then chlorine is in group 17 or 7A, and it wants to form a negative 1 charge. And so we're going to have 2 chlorines dissociated. We're going to have 2 chlorine ions formed from the dissolving of calcium chloride, because we see that 2 as a subscript after the Cl in the reactants. And so That means that when it dissolves, we're going to form two chlorine ions. And so in number one, the answer would be choice C. We'll have one calcium ion with a positive 2 charge and two Cl minuses or chlorines with a negative 1 charge. So when it dissolves, you're not going to have that subscript anymore. That subscript becomes a coefficient or written in front of the chlorine, the Cl minus. In number two, we have potassium phosphate, and again, that is an ionic compound. And so here, you'll have to remember that the PO4 group, the phosphate, is a polyatomic ion. So that is going to stay together. The PO4 stays together. And so that's why we did mention polyatomic ions. We didn't go specific into that, but you have to recognize them. And so when potassium phosphate dissolves and dissociates, it's going to break up into 3 potassium ions, and then it's going to break up into the phosphate. And the phosphate has a negative 3 charge. And so our answer is going to be choice A. All right, so the PO4 is going to stay intact, but it's going to have a negative 3 charge, and when it dissolves and dissociates in the water, it's going to be an aqueous solution. And so our answer is going to be choice A. And so that's what we can see here. Okay, so just you'll have to recognize those polyatomics, and remember that they have to stay intact and stay together when they dissociate. Weak electrolytes will dissolve in water, and when they do, they will form some ions. So it's not going to completely dissolve. It's not going to completely dissociate or separate into its ions. And because of that, when we write the chemical equation, we see a double arrow. Um, and so that means that we are going to make some ions, but those ions can then reform into the original reactant, and so it just kind of goes back and forth, and so we're not going to go completely from reactants to products. It's going to be able to go backwards as well, and so you're going to have some of the reactants and some of the products in the solution at one time. And so we'll have some ions and some molecules. So that's why we see that's why we call it a weak electrolyte, because it does have some ions to be able to pass electrons through the solution, but it's not going to be completely. It's not going to be as many electrons or as many charges in the solution, and so that's why that light bulb is not going to be able to light up as bright as we saw in the previous pictures. And non-electrolytes, they still dissolve in the solution, but they do not dissociate. They do not separate into ions. And so um, when we show that in a chemical equation, we show that it's changing physical states from solid to aqueous, but that is all. We do not break up that molecule at all. And so because it does not have any charges in the solution, that's why we do not see the light bulb being able to light up, because there's nothing to light it up. There's no electrons or negative charges to be able to conduct the electricity. And so this is just a nice table that kind of summarizes what the differences between these different types of solutes. And so a strong electrolyte completely dissociates, weak electrolyte partially dissociates, non-electrolyte does not dissociate at all. So in a strong electrolyte, we'll have ions. Weak electrolyte, we have ions and molecules. Non-electrolyte, only molecules. And so strong electrolytes are able to conduct electricity because of those ions, because of the complete dissociation. Weak electrolytes weakly conduct electricity, so you'll see the dim light bulbs. And so and that's because there are some ions, but not many. And then non-electrolytes cannot conduct electricity because there's no ions. And so strong electrolytes are typically salts, any type of ionic compounds, any kind of strong acids and strong bases. Weak electrolytes can be thought of as weak acids and weak bases, and we'll get into that later on in the course. And then non-electrolytes are typically carbon-containing compounds and that are still able to dissolve in a solution. So this brings us to talking about equivalence. And so an equivalent is just the amount of charges that will be in that will be made from 1 mole of solutes. So how many total charges are you going to be able to make from 1 mole of that compound dissolving in the solution? So we'll look at, in this case, in this first example, sodium chloride. So when sodium chloride dissolves in solution, you have Na plus and Cl minus. And so when you dissolve NaCl in solution, you'd be able to form 1 mole of sodium ions and 1 mole of chlorine ions. They would both have one equivalent. And so in total, you would have a two equivalents because you would have Na and Cl. So here so you're just basically looking at how many moles of the of each ion are you going to create, and what are the charges of those ions. And so on the little table on the bottom, you see that if you have sodium Na plus, that 1 mole of Na plus, one equivalent, because we have just a positive one charge. If we have 1 mole of calcium ions, because calcium has a +2 charge, we have two equivalents. If we have 1 mole of sulfur ions, sulfur has a -2 charge, and we have 1 mole of it, so it's going to be two equivalents. And so you're basically looking at how many moles of the ions you have and what are the charges of those ions to be able to figure out the equivalence. So electrolytes are important for maintaining proper functions of our cells and organs in our body. We need sodium ions, we need potassium ions, we need bicarbonate ions, and they tell you why we need all these different things for different processes in our bodies. You know, if we always hear about electrolytes when we are buying sports drinks, you know, to replenish the electrolytes in our body so we can keep hydrated and keep all of the electrolytes in our body to, you know, keep us at our peak performance. And so, you know, electrolytes are important for our bodies. And so this just kind of goes through and gives you the concentrations and the equivalents of each of these different electrolytes in our body. And so if you're interested in that, you can see the table here. So here it just kind of wants us to go through how many equivalents there are for each of these examples. So if we have 1 mole of iron ions that have a +3 charge, we have to multiply the moles times the charge. And so we have 1 mole times a +3 charge, and we get 3 equivalents. And so that would be choice C. In number 2, it says we have 2.5 moles of the sulfate ion, which has a -2 charge. And so we had to multiply the moles times the charge. So 2.5 times the 2, we would get 5 equivalents, which would be choice B. And then if we have an intravenous bottle containing only salt, and we have a 34 milliequivalents per liter of sodium, then we should have the same amount of chlorine equivalents, because when we dissociate NaCl, when we put NaCl in water, we break it up into one Na plus and one Cl minus. So they should be of the same concentration. And so it should be choice A. And so we can see some of that worked out here. So here's another question that we can look at, another example, and it says the laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. And so in A, it wants us to first determine how many moles of calcium ions are in 0.5 liters of blood. And so we're trying to figure out the moles of the calcium. And so first we need to figure out the equivalents. And so we know that we have a half of a liter, and we know that we have 8.8 milliequivalents per liter. And so what we first want to do is be able to figure out how many milliequivalents. So we would multiply the volume by the concentration to get our milliequivalents, and then we just need to um, uh, figure out how many equivalents from the milliequivalents. So we just need to use our conversion factor. And so when we shows the work here, we get a number of 0.0044 equivalents of calcium ions. And so because calcium has a positive 2 charge, for every 1 mole of calcium, we're going to have 2 equivalents of calcium because of that charge. And so what we need to do to figure out number of moles is we need to multiply the 0.0044 equivalents by that that ratio. 1 mole of calcium would produce 2 equivalents of calcium plus 2. And so we get 0.0022 moles of calcium plus 2. And so then in B, it asks if the chloride ion is the only other ion present, what would be the concentration of the chlorine ions, or the chloride ions, in milliequivalents per liter. And so So the easiest way to figure out the chlorine minuses milliequivalents per liter would just be, it would have to be equal and opposite to the calcium plus 2. You would have the same concentration of charge from the of the chlorine to the calcium, and so it would just be 8.8. And so that just works out because we would have 2 moles of chlorine for every 1 mole of calcium, but chlorine only has a -1 charge. And so the equivalents are the same for chlorine as it is for the calcium. And so it works out that we would have the same concentration of the milliequivalents per liter from the chlorine as the calcium. And so in 8.4, we're discussing solution concentrations, and so this is a very important part of solutions, and a lot of calculations are based off of these concentrations, and so it's going to be very important to understand how we can calculate these different concentrations and the different ways to represent concentrations. So a concentration is just a measurement of how many solutes, how much solute you have in a certain amount of solution. And so the 4 most popular or most commonly used concentrations are mass percent, volume percent, mass per volume percent, and molarity. So mass percent is comparing the mass of the solute to the mass of the solution. And the solution is made up of solute and solvent. So we can write it in either way, as we see here. Mass percent is equal to mass of solute divided by the sum of the mass of solute and solvent, or mass percent is equal to the mass of solute divided by mass of solution, both of which are multiplied by 100% to be able to figure out the mass percent. And so here's just an example. If we're trying to determine the mass percent of KCl in water, if we mix 8 grams of KCl with 42 grams of water, and so the solute is the KCl, and so our mass of the solute is 8 grams of KCl. And then we have to figure out the mass of the solution, and so the solution is made up of KCl and water, so we're going to have to add together the KCl and water, so it'd be 42 plus 8, which would be equal to 50, and so that would be the mass of the solution. So we would take 8 divided by 50 times that by 100 to get 16%. And so one thing, if you plug it into your calculator, if you do 8 divided by 50 times 100%, it probably will give you something different. So what you want to do is when you plug it into your calculator, do 8 divided by 50 times 100, and that will be the percent. So do not press the percent button when you multiply it by 100. All right, so multiplying it by 100 will give you the percent. And so sometimes people get tripped up by that. So your percents, so just don't press that percent button. It's not needed. So here's just kind of a flow diagram of showing how we could go and calculate the solution concentration. So we typically want to state the given quantities and then state what we're trying to figure out, or the needed quantities. Then we can write out the concentration expression, or the equation, and then we just substitute our quantities into the equation and try to calculate. And so here we have 15 grams of sodium carbonate and 235 grams of water. What is the mass percent of sodium carbonate in solution? So what we are given is the mass of the solute, which is 15 grams of sodium carbonate. We know that we have 235 grams of water. And so the total solution, we're looking at mass percent, so we need to know, and we're trying to figure out mass of solute divided by mass of solution times 100. So we can write out our equation. And so what we'll need to do is, we know the mass of the solute, which was 15 grams, and so we would have to go and figure out the mass of the solution. And so the solution is made up of sodium carbonate and of water. And so we would have to add those two together, the solute and the solvent. So 15 plus 235 is equal to 250. And so then we can divide 15 by 250 and then multiply it by 100, and we would get 6% mass by mass of sodium carbonate. So here it's asking, what is the mass percent of sodium hydroxide in solution prepared by dissolving 30 grams of sodium hydroxide in 120 grams of water? And so what we want to do is we want to state what we know and what we're trying to do. And so we have 30 grams of the solute, which is the sodium hydroxide, in 120 grams of water, which is the solvent. And so we go ahead and calculate the mass of the solution, and that would be both of those quantities added together, which would be 30 plus 120, which would give us 150 grams of sodium hydroxide. And so then we know our expression or equation is equal to is mass percent is equal to grams of solute divided by grams of solution divided by times 100. And so the mass of the solute is 30 grams. Our mass of solution is 150 grams. And then we multiply that by 100, and we get 20% sodium hydroxide. We also have volume percent. Volume percent is done much of the same way, except that we're using volumes. And so in this case, or given, if we have a 7% volume by volume solution, that means we have 7 milliliters of solute divided by 100 milliliters of solution. So it's done exactly the same way as mass percent, except that we're using volumes. So if we have 59 milliliters of lemon extract solution, and that contains 49 milliliters of alcohol, what is the volume percent of alcohol in the extract solution? So what we would want to do is we want to first write out what we are given. We know the solute, what we're looking for. It's asking for the volume percent of alcohol. So that is our solute, 49 milliliters of alcohol. We know that we have 59 milliliters of solution. And so that is, it gives us the total volume of solution. And we're trying to figure out the volume by volume percentage. So we write out our equation. Volume of solute divided by volume of solution times 100. So our volume of solute was 49 divided by our volume of solution, which is 59. Multiply that by 100 and we get 83% volume by volume percent. So now we are brought to mass volume percent, and mass volume percent is just comparing our mass of solute by our volume of solution. And so we want to remember to use grams of solute and milliliters of solution. Before, we always wanted to use the same units. It didn't matter if we had grams per grams or kilograms per kilograms. It didn't matter if we had milliliters per milliliter or liter per liter, because the units would just cancel out. As long as we had the same units, it would be fine. But here, now we have different units, so we need to make sure we have grams per milliliter. And so we're going to, so in this case, when we have a 5% mass volume percent solution, that means we have 5 grams of solute per 100 milliliters of solution. And so we just need to make sure we have our mass in grams and volumes in milliliters. So in this case, in this example here, we see that if we add 5 grams of potassium iodide, and we make 250 milliliters of water, what we would do is put the 5 grams of potassium iodide and fill up the volumetric flask to 250 milliliters, and then we would get a mass volume percent of 2%. And so that is done, shown here. The work is shown here, and what we do is, we have to state what we are given. We're given 5 grams of potassium iodide solute. We have 250 milliliters of potassium iodide solution. And so we are going to use the equation grams of solute divided by milliliters of solution. And so 5 grams divided by 250 milliliters times 100 will give us that 2%. And the last one we'll talk about is molarity. Molarity is most commonly used in chemistry. The other ones you typically see, in more everyday practices. But when we're going over, when you see questions in textbooks and things like that, typically you'll see molarity. And so molarity is a concentration that describes how many moles of solute you have in a liter of solution. And so if we have 2 moles of NaCl dissolved in 1 liter of solution, we would have a 2.0 molar solution of NaCl. So we would have 2 moles divided by 1 liter, which would give us 2 molar. And so how you would do that, you would have to figure out your mass required for NaCl to have 2 moles of it. And so once you figure that out, you would add that 2 moles of salt into the volumetric flask, and then fill up that volumetric flask to the 1 liter mark to make your 2.0 molar concentration solution. And so if it's asking us here, what is the molarity of a 0.350 liter solution that contains 46 grams of potassium chloride, we want to write out what we are given. We're given 46 grams of calcium chloride. That is our solute. And we have 0.35 liters of solution. And so we want to figure out molarity, which is moles of solute divided by liters of solution. So before we can just plug away, we need to be able to determine how many moles of potassium chloride we have. So we need to calculate our molar mass of potassium chloride. And so potassium chloride has a molar mass, a molecular weight of 74.6 grams per mole. And so we're going to use that. We're going to take our 46 grams of potassium chloride and use our conversion factor here of 1 mole of potassium chloride would be equal to 74.6 grams of potassium chloride. And so then that would give us 0.62 moles of potassium chloride. And so now we have everything required to be able to plug into our equation. So our equation for molarity is moles of solute divided by liters of solution. So we just solved for the moles of solute, which was 0.62 moles. And we had the liters of solution stated in the question, which was 0.350. So we take our 0.62 and divide it by 0.350, and we get 1.8 molar KCl. So this is just a table that that shows what units that you'll need to compare your solutes to your solutions in these different concentration expressions. And so when we use mass percent, typically is grams per grams, but as long as you have the same units of mass, it does not matter because those units will cancel out. You can use kilograms per kilograms or milligrams per milligrams. It does not matter because they will cancel out. But typically it's used grams per grams. Volume percent, typically it's milliliters per milliliter, but like I said before, it does not matter as long as they are the same unit, liters per liters, whatever. Mass percent, it's easiest to do grams per milliliter. So that's typically what's done. And then molarity is moles per liter. So those, you want to try to use those units. So here it's asking us to calculate the molarity of 60 grams of sodium hydroxide in 0.25 liters of solution. So it's much like that previous question that we had done. So we want to state out what we're given. We're given 60 grams of solute, NaOH, and 0.25 liters of solution. We know our expression is moles of solute divided by liters of solution, but we can't just simply put those numbers in there because we don't know the moles of solute yet. So what we need to do is we need to figure out the molar mass or the molecular weight of sodium hydroxide, NaOH. And so we use our periodic table and we calculate that 1 mole of NaOH has a mass of 40 grams. So use that conversion factor, and we get 60 grams of NaOH times 1 mole of NaOH per 40 grams of NaOH would be 1.5 moles of sodium hydroxide. And so now we have our moles of sodium hydroxide, so we can plug that into our equation. And so we get 1.5 moles of NaOH divided by 0.25 liters of solution. And so we get 6 molar. All right, so just make sure that we have moles of solute and liters of solution. Because we see here, sometimes they give us grams of the solute, so you need to convert it. And sometimes it will give you milliliters of solution, so we'll have to convert that if it's ever done. And so here is just showing another factor of different ways to use these concentration expressions, and there are different ways to represent their conversion factors in case we need to go back and solve for something other than the concentration. If we need to go back and calculate the mass of the solute or the volume of the solution, things like that. So you can write it out in this way. So if they give us the percentages, if the mass percent, the volume percent, or the mass per volume percent, you just take those percents and put that per 100 of that measurement of solution. So in 15% of KCl, we have 15 grams of KCl in 100 grams of solution. For a 12% volume by volume ethanol solution, it's 12 milliliters of ethanol per 100 milliliters of solution. For 5% mass by volume glucose solutions, 5 grams of glucose per 100 milliliters of solution. And then lastly, molarity, we have 6 moles per liter. And so we can just use that as a per liter number, a conversion factor. All right, so here we're just practicing writing out the conversion factors for each of these. And so for number 1, if we have 8.5% mole mass by mass of sodium hydroxide, we could just show these conversions here. It'd be easier to explain. We have 8.5 grams of NaOH per 100 grams of solution. Or we could write it just the opposite. In 100 grams of solution, we have 8.5 grams of NaOH. If we have 4.8% mass by volume of HCl, that means we have 4.8 grams of HCl per 100 milliliters of solution. Or equally, in 100 milliliters of solution, we have 4.8 grams of HCl. And then for 3.4 molar NaOH, we would have 3.4 moles of NaOH per liter of solution, or in 1 liter of solution, we have 3.4 moles of NaOH. So we just need to know how to write out these conversion factors in case we need to use them in solving some problems. And so that's what we're going to be doing here. So if we are trying to use these concentrations to calculate mass or volume. So we always want to first state out what we have and what we need to get. Write out a plan to figure out how we're going to get what we need. Write out any of our conversion factors and then set it up to solve. So here it's asking us to calculate how many grams of NaCl are needed to prepare 225 grams of a 10% mass by mass solution of NaCl. So we want to write out what we're given. We know we have 225 grams of the NaCl solution. So that's our mass of solution. We know that we have 10% mass by mass NaCl solution. And we need to get grams of NaCl. So what we need to do is write out our plan. We need to go from grams of solution to grams of NaCl by using our mass by mass conversion factor. Write out our conversion factor. So in 10 grams of NaCl, we have 100 grams of solution, right? So that's when you have 10% mass by mass percent of NaCl, means when we have 100 grams of the solution, we have 10 grams of NaCl. So then we can now set up our problem, right? We can it's probably easiest to make sure you write out your complete units so you can watch and see where the units need to cancel out. So we know we want our grams of NaCl solution to cancel out, and we want to be left with grams of NaCl. So we're going to have 225 grams of NaCl solution times the 10 grams of NaCl divided by the 100 grams of NaCl solution. And we can see our grams of NaCl solution canceling out. And we're left with grams of NaCl. And we get 22.5 grams. In the next one, we're asked to calculate how many liters of a 2.0 molar solution of NaCl are needed to provide 67.3 grams of NaCl. So this is going to be kind of a double step. And so we'll see why that is. So we are given how many grams of NaCl and the concentration of the solution, and we need to get the liters of solution. And so first we need to figure out how many moles of NaCl we have, because in order to use our concentration, our molarity, we have to have moles. And so in order to go from grams to moles, we need to use the molar mass of NaCl. And then in order to go from moles to liters, we need to use the concentration. So we use our periodic table to find the molar mass of NaCl, and we find it to be 58.5 grams per mole. And then we know that the other equality that we'll have to use is that 2.0 molar solution means that we have 2 moles of NaCl per 1 mole of NaCl solution. So then we can set it up. We know we want to be left with liters of solution. You can break this up into 2 steps, and that's how I typically do it. But here it's done in 1 step. So we know we want our grams of NaCl to cancel out to get our moles of NaCl. So we multiply 67.3 by 1 mole per 58.5 grams of NaCl. And then we would multiply that by 1 liter of NaCl solution has 2 moles of NaCl. And multiplying those values, you would get 0.575 liters of solution. And now we'll get into properties of solutions and how these properties affect solutions. And so we are just going to really look at these 3 different types of mixtures. We've already talked in length about solutions, but we'll also have different types of mixtures called colloidal or colloids, or sometimes colloidal dispersions, and then suspensions. And so these really go into, we've already talked about solutions and how they're homogeneous mixtures, and this is really going into discuss why colloids and suspensions are different, and has to deal with the particle size and their distributions. So in a solution, we know that we have these small particles, and they are dissolved in the solution. They are dispersed equally and evenly throughout the solution, the solvent, and you make a homogeneous solution, so it's the same throughout. You will not be able to see the solutes and solvents. It's just going to look all together and be mixed evenly. So there's no real distinction between the two. You just have a solution. You don't have really solute and solvent. You don't be able to see the differences. And so these solute particles are just so small that you won't be able to separate them by simply using filters or membranes. Whereas colloids are different because they do have large solute particles, much larger than in solutions. They are homogeneous mixtures that are not able to separate or settle out. So you won't see them having any type of buildup anywhere. But the difference here is that the solute particles are large enough to be stopped by semi-permeable membranes, but they can pass through filters. So this is basically the only difference between colloids is that they are larger solute particles and they can be separated by semi-permeable membranes. So semi-permeable, semi means um, you know uh, kind of. It can be it's selective, and permeable means it allows to pass through. So semi-permeable, some things are able to pass through these membranes. That's what that means. And so, and using these particular types of membranes, these solid particles are too large to be able to pass through them. And so, some examples of colloids are, fog. Fog, we have liquids and gases. When we have smoke, we have solids and gases, and so and we see all these other different types of colloids. And so we know that when we have these different colloids, that you know they are homogeneous mixtures. They are consistent throughout the colloid, but we are able to separate them using semi-permeable membranes. We can't filter them out, but we can use these membranes to be able to separate out some of these solutes. Suspensions are different because they are not homogeneous. They are heterogeneous. They are not uniform mixtures. They are not the same throughout. They have very large particles, and these large particles can be both separated out by using filters or semi-permeable membranes. So they are different from colloids because they are not homogeneous, and they can be separated by using filters. If you let these suspensions basically sit for a while, the solutes can settle to the bottom. Um, and so you need to continually stir them so that they stay suspended and stay in solution. And so sometimes we have, when it says, shake well before using or something, those are usually because they are a suspension. And so these are different this is a nice table summary of these different types of mixtures, solution, colloid, suspensions. And so one thing we can look at is the size of the particles and molecules. So solution, very small, colloid, large, suspension, very large. You can look at the settling. Solutions and colloids do not settle, suspensions do settle. And then you can compare the separation techniques. Solutions cannot be separated by filters and membranes. Colloids can be separated by membranes but not filters. Suspensions can be separated by membranes and filters. And so here's just a nice little picture of showing these differences. So when we have these different mixtures all in solution together, we see that the suspensions will settle out. We can use a filter to separate out the suspensions, and then we can use a semi-permeable membrane to then separate out the solutions from the colloids. All right, and so here's just kind of double checking a mixture that has a solute particles that do not settle out but are too large to pass through a membrane, and that would have to be colloid. All right, suspensions settle, solutions cannot be separated by membrane. And so that's what we see here. So we have a colloid indeed.